The Azide synthesis is a way to turn an alkyl halide into a primary amine. We've been accomplishing this so far in this chapter using the Gabriel synthesis. But if you don't have phthalimide as a source of nitrogen, then you can still do an SN2 reaction to turn an alkyl halide into an amine by doing this azide synthesis. Now you can only make primary amines this way. The recipe that you'll always use has 3 steps. The first is you're going to treat your alkyl halide with a molecule called sodium azide, NaN3. We'll talk about what that looks like and how that behaves in just a second. Once you have that there, that creates the new carbon to nitrogen bond. Once you have that, you add lithium aluminum hydride, so you're doing a reduction, and then you just shake it up with some water. Do a water wash to stabilize any charges that form there in the reduction step. Okay, so that might look a little strange, so I want to very quickly walk through the mechanism for this reaction. And it all starts with sodium azide. That's going to be our source of nitrogen. Around 250 billion tons, oh my gosh, 250 tons, forgive me, 250 billion tons would be insane. Around 250 tons, so around 250,000 pounds of sodium azide are produced industrially every year. And that's because sodium azide is useful for the same reason that sometimes you don't want to use it in the lab. It's explosive, and it creates a lot of gas. So gas just bursts out from it if it's shaken too hard or if it's put under any type of stress. And so you might be wondering, why would anyone want to produce this explosive compound, which, by the way, is extremely toxic? It seems like it'd be a nightmare to work with in the lab, and it kind of is. But anytime you see something, you want to see it from as many perspectives as you can. Something that's a liability in one situation is an advantage in another. And you can use this molecule that explodes gas in things like airbags, or to inflate the slides, the emergency slides on airplanes. And that's largely what sodium azide is used for. So there are a lot of people who die from having been exposed to sodium azide, but they're not people who, it very rarely gets out of the airbags in cars. The fatalities are almost never from that. So this is what sodium azide looks like. It's a crystalline solid, and in terms of the molecular structure, you have sodium, which is just acting as a counter ion. The positive charge is trying to stabilize a negative charge on this nitrogen. Now it's strange because you have 3 nitrogens bonded to each other. And something that it's worth pointing out as many times as we have an opportunity to is that organic chemistry is the chemistry of carbon. And carbon is special because it can form stable bonds to itself in long chains. That allows it to form infinite shapes, and the relationship between those shapes encodes the messages of life. And so whenever you see other molecules trying to form long chains of bonds to themselves, you should think, that is not a stable molecule. That is going to burst apart. And that's the case in the case of azide. Now, this nitrogen, the nitrogens on the ends only have 2 bonds and 2 lone pairs. That means that they have a negative charge. And the nitrogen in the middle has 4 bonds and 0 lone pairs. That means it has a positive charge. So really unstable molecule. You could see why it would burst. It would be a little tricky to work with because it's so unstable. But what's going to end up happening is you can take your alkyl halide, and it's going to undergo an SN2 reaction with one of the nitrogens in the azide. So one of those negative nitrogens can act as a nucleophile, can attack the carbon in the alkyl halide and kick the leaving group off. And so that would be our SN2 reaction. And what we have after that step would be our leaving group will have left, and here, I'm just going to draw this to the other nitrogen. The molecule is symmetrical. Here, we will have a new nitrogen to carbon bond. Actually, let me do that. Okay, so a new nitrogen to carbon bond. All right, well, that's the first step, adding sodium azide to your alkyl halide. After that, we want to replace all these bonds between the nitrogens with bonds to hydrogens. And so we can use a reducing agent like lithium aluminum hydride and follow it up with a water wash. So if you have lithium aluminum hydride, remember that the structure for lithium aluminum hydride is you have aluminum in the center, 4 hydrogens bonded to it. That whole thing has a negative charge. And the negative charge is stabilized by a positive lithium cation. Now, aluminum is a metal, so it has very low electronegativity. It's going to lose its electron density to the hydrogens. The hydrogens are going to become slightly negative. That means that those nitrogens can act as nucleophiles, hydrogen nucleophiles. Now this nitrogen here is really trying to pull electron density from the other nitrogens. It's electronegative itself, sure, but it has this positive charge that's really unstable, trying to steal electrons to stabilize it. And so this nitrogen would easily give up its electrons to give to this positive carbon, or positive nitrogen, if it just got a little push. And that's what happens in this first reduction step. A hydrogen attacks this nitrogen here and pushes these electrons in that unstable pi bond between 2 nitrogens onto the nitrogen with the positive charge. So what ends up happening is that pi bond turns into a lone pair, and this lone pair turns into a bond to a hydrogen. Okay. So now, oh, excuse me, yeah, this lone pair is not involved in the bond. It's these electrons that make the bond. This lone pair is still there. It's just there as a separate lone pair at the bottom. So now that we've done that, we have a bond that's really unstable. It's between this here. And so those electrons can easily get pushed off. Remember, any bonds between elements that are the same are usually unstable. Carbon is very unique in that it forms stable bonds to itself. And these electrons are unstable too with their negative charge. So they go to form a third bond here and to kick off this nitrogen. Oops. So we end up with 2 things at this point. We end up with something that's really close to the amine that we want. And then we end up with the explanation for why this is used in airbags. This is N2. It's molecular nitrogen. It's nitrogen gas. If you want to know what that looks like or feels like, just inhale right now. 79% of the air you're breathing is this molecule. Only 19% is oxygen. And this is the gas that's released when this sodium azide explodes. It's the gas that pushes out the airbags in a car. So you can see that inherent in this azide is the potential to release a molecular nitrogen, which can leave as a gas. Now this other nitrogen, on the amine that we want here, has a negative charge, and that's why we do the water wash, to do a proton transfer from water so that steals a hydrogen, the electrons snap back onto the oxygen, and we end up with our amine. So I wanted to quickly walk through the mechanism for that because we haven't seen azide before, and the mechanism is a little strange. But on the whole, the idea is that you have an SN2 reaction followed by a reduction with lithium aluminum hydride. Okay, well, exercise 2320 is asking us to make all the same molecules that we've made in the last 2 videos. but using sodium azide as your source of nitrogen. Now remember that we can only use this azide synthesis to make a primary amine. After that, we would have to use reductive amination. Now, because the last couple of videos were very long and went through the exercises in great detail, and because this would largely just be a repetition of that, what I have here are the synthesis for this molecule from the previous video, where we used the Gabriel synthesis in this top step to make the primary amine. Well, if we're not going to use phthalimide as our nitrogen source, but instead we're going to use sodium azide as our nitrogen source, that's going to be the only difference in the synthesis that we came up with last time. So we'll get rid of the parts that are unique to the Gabriel synthesis. We'll take the alkyl halide that we figured out in the last video, and we can turn that alkyl halide into the primary amine by adding those three steps that we just discussed. First, sodium azide. Second, lithium aluminum hydride. And third, water. Now, you'll want to go back and review that last video to figure out how we got these pieces, this piece and this piece, from the original molecule that we wanted to make. But once you understand the previous video, you can look at this one, maybe in a new tab, side by side, and you can see that we can make this primary amine by using the azide synthesis and the alkyl halide, the same alkyl halide that we would have used in the Gabriel synthesis. We can do the similar thing for B. We can take the synthesis that we developed in the last video to make the primary amine. So that was our Gabriel synthesis. But here, we don't want phthalimide as our source of nitrogen. We're going to use azide, sodium azide, as our source of nitrogen. So we're going to erase everything that is unique to the Gabriel synthesis. We'll keep the same alkyl halide that we had before, but we're going to treat that alkyl halide first with sodium azide, then with a reducing agent, lithium aluminum hydride, and then with water. And that will accomplish that transformation. That will turn this alkyl halide into a primary amine. Okay, let's try it for C. Now here's the synthesis we came up with in the previous video for C. It has a couple steps. The first step was the Gabriel synthesis. That's the step that we're going to modify here. After that step, we used reductive amination to connect the carbon chains, the other carbon chains, to the nitrogen that we had. So for an explanation for this reductive amination, you can view the last two videos. That was explained twice in the last two videos. But for this first process, to make the primary amine, we can replace the Gabriel synthesis with the sodium azide, or with the azide synthesis. Instead of using phthalimide as our source of nitrogen, we can erase everything that's unique to the Gabriel synthesis, all these unique recipe, but we take the same alkyl halide and we just add first sodium azide, followed by lithium aluminum hydride, and water. And you'd be really careful mixing these things in the laboratory because they would be potentially explosive and very toxic. So that allows us to replace our alkyl halide with an amine, a primary amine. Once we have the primary amine, we can do two steps of reductive amination, as we discussed in the last two videos. Okay, how about D? So for D, this is the synthesis we developed in the last video. And the first step, creating the primary amine, we used the Gabriel synthesis for. That's this part in orange. The second step was a reductive amination, and we discussed that and how to come up with that in the last two videos. So in this one, I just want to point out that you can replace the Gabriel synthesis with the azide synthesis. Instead of using phthalimide as the source of your nitrogens, you can use sodium azide. So we'll erase all of these reagents that are unique to the Gabriel synthesis. Oops. And we'll use the same alkyl halide, but we can turn that into an amine. We can turn that into the amine here, basically replace this with an amine, by adding first sodium azide, NaN3, and then strong reducing agent, lithium aluminum hydride, and then water. And that would create that transformation using the same mechanism that we drew at the beginning of this video. Once you have that primary amine, you can do a reductive amination to create a secondary amine. And that's the amine that we wanted here. And we discussed this step in the last two videos. Okay, E. Now remember, these are the same exact molecules in the last two videos, so we came up with the exact syntheses for them. But we used the Gabriel synthesis as the source of our nitrogen. So we have the Gabriel synthesis here to make a primary amine. After that, we did reductive aminations to make a secondary and tertiary amine. So if instead of using phthalimide, we could use sodium azide and do the azide synthesis. So we would erase all the reagents that are unique to the Gabriel synthesis. We would take our alkyl halide, the same one, and we can turn it into an amine, a primary amine, by doing the azide synthesis, adding sodium azide, NaN3, followed by lithium aluminum hydride, and then a water wash. So that allows us to create a primary amine, and once we have that, we can turn it into a secondary amine by doing a reductive amination, take that, turn it into a tertiary amine by doing another reductive amination. We discussed that part of this exercise in the last two videos. Okay, let's focus on this azide synthesis one last time. This is the synthesis we came up with in the previous video for how to make this amine that we have here in F. And the first step, making the primary amine, in the last video we used the Gabriel synthesis. Our nitrogen source was phthalimide. So we can make our primary amine with a different nitrogen source, sodium azide, by doing the azide synthesis. So we can erase everything that's unique to the Gabriel synthesis. You'd take the alkyl halide that you wanted, and we figured out how to get that in the last two videos. And just instead of adding the reagents, the recipe for the Gabriel synthesis, you'd add the recipe for the azide synthesis. First, sodium azide, NaN3. Second, lithium aluminum hydride. And third, a water wash. That'll create your primary amine. Once you have that, you can do a reductive amination to make it a secondary amine, and then another reductive amination to make it a tertiary amine. And we discussed those steps in both of the last two videos. So in this video, we introduced the azide synthesis, walked through the mechanism for it, and then we applied it to a bunch of problems. Now, we took the syntheses that we had, that we developed in the last two videos, and we just changed the first step. We changed how we made the primary amine, because that's all the azide synthesis can make is a primary amine. So we took the alkyl halide that we would have used in the Gabriel synthesis, and reacted that first with sodium azide, followed by lithium aluminum hydride, followed by a water wash. That gave us our primary amine, which we could then turn into secondary and tertiary amines using reductive amination.